So far we've covered the electrical part of electromagnetism, but today we're going to cover magnetic field. Now for some reason Dave called this B, so we're going to go with that. But we also need to know something else. This is mu naught, and that would be 4 pi e to the negative 7, and then this is going to be in Tesla meters over amps. This is the permeability constant that we're going to need for some of these equations. What that basically means is if the magnetic field is starting to form in empty space, then there's going to be a resistance to that formation, which is this value here. All right, and the most important rule we need to think about is we're going to point our thumb in the direction of the current, and that will give us the direction of the magnetic field. So if we have the current going like that, we're going to do the right hand rule, and as you can see, if I put the thumb in the direction at the top, it's going to be pointing this way, and it will be greater as it's closer, and it'll start to diminish as it's further away from this current. And of course, if you were to switch that and go on to the other side, direction, bam, you could start to see how this will basically just rotate around. Bam, start to get smaller, and bam, and get smaller. Now we can represent this with the Savart Law equation, which is basically going to say dB equals the mu naught over 4 pi, and then we'll have the IDS cross R divided by R squared, and this is going to be in Tesla. Now, Tesla is kind of a weird unit. That's basically Newton over amp meters, or you could say Newton seconds over Coulomb meters, or kilograms over amp seconds squared. So it's kind of a strange unit. Now let's figure out what this whole Savart law is trying to tell us. Let's set up a problem here. We're going to try to figure out the magnitude and direction of the magnetic field at this particular point. Now we're at a distance from a wire here, and the current is going to be going essentially in this direction here. I'm going to draw the arrow with the I, and this is actually a small little distance in the I direction, which is going to be that component right there. And I put that point right here, starting there. We're also going to cross that with the R vector. That R vector is going to be pointing towards that P point like this, and it's essentially going to follow that line right here, which we would usually call R, and then this would be the R unit vector right there. Now when we cross that, we're supposed to be getting an angle here, right? So this would be the angle theta right here, and then this would be your R vector. But we also know that over here, this would be pi minus theta, and since it's a cross product, well, let's set this up. We'll go dB is supposed to be equal to the mu naught, and then it will be an I, and then put the 4 pi down there. We're going to integrate this. We're going to use that dot product on top, which would be ds, and then R vector 1, and then sine theta. So the unit vector is just 1. It's kind of like ds r sine theta, right? That's how you would do the cross product. Now sine theta is going to be this thing right here. But just so you know, sine of theta is sine of pi minus theta. Those two things are exactly the same. So it really doesn't matter whether you take this angle or that angle, you get the same answer. That makes things nice. You can kind of interchange things. And also this R, if we were to say what R was, well, R squared is actually going to be x squared plus y squared. So let's just keep that in mind. And so we'll put that over here, x squared plus y squared. And then we can try to replace this sine theta with actual numbers, because again, like we're just going with that angle, like how are we going to take the sine of that? There's nothing out there. But we can take the sine of this angle. It's a little bit easier. We got the x over r. So that would be x divided by the square root of x squared plus y squared. All right, and so that way we can set up our b over here at this point. And if we try to figure out what direction that would be pointing, well, there's two ways we can do this. First, you can use this rule. So you point your thumb in the direction of the current, and you would move it this way. So you'd figure out that it is going into the page this way, like this. So that's one way you can do it. Or the other way is that you can take this cross product thing, and you can just say, okay, well, I'm going this way, and then I'm going to well, I'm going to be crossing it this way. So you can see again, it's going to point into the page. Both of those ways will get you the proper direction. And as far as what that b is, well, we start with the mu naught I 4 pi, because that's outside the integral. We're going to go 0 to L, and then we're going to have, put that x on there. We've got the x on top, and then you've got on the bottom, it's going to be this square root times that normal thing. So you'll basically just get x squared plus y squared, and then 3 over 2. And this is going to be over dy in this particular situation. So, yeah. Now, I'm not going to go through with the entire integration here, but there are a couple of important answers that we kind of need to go for. The first one is going to be I'll just call this bx. Mu naught ix divided by 4 pi d. If this is a long straight wire, meaning 0 to infinity. Now, you might actually have to multiply this thing by 2, so just keeping that in mind. But essentially, from 0 to infinity there, if we were to calculate that point right there, d, x is d, distance away, then the magnetic field would be equal to that. You'll notice that there's no length. The length will basically just go away. It's infinite length. But if this would go also extend in that direction, in both directions, then you're going to want to multiply that by 2, because you'd have impact from that side, impact from that side, so you get double times that. So this is just if this L goes to infinity. And then I'll have another one. Bx is equal to mu naught Ix divided by 4 pi d, and this would be L divided by square root of d squared plus L squared over 4. That top part just slightly nicer with the L on top. And this is essentially going to be a perpendicular bisector formula. So that would be if you have this length L here, and you wanted to figure out right in the middle here, length there. This is not an infinite length, by the way. This is an actual length from 0 to L, and you want to figure out the perpendicular bisector right there. Essentially, if you would go from negative L to L, the answer, it would be the answer to this integral, essentially. That would be the distance d. Well, yeah, so that would be the answer to that integral. Let's look at a couple more really important answers, which would be something like a circle or an arc. If this was going from 0 to pi over 2, we're going to make sure that all of our arc measurements here, or angle measurements, are in radians. So I'm just going to put that right here, radians. So that's a key to this. But the idea is that, yeah, so if it wasn't perfectly straight, if it was like a little bent one like this, then let's go ahead and draw our eye going like this. This is the IDS. And then we'll also draw the R vector. That would be pointing right there towards the center. So here's the R. And then here is the radius, just regular R. And if we wanted to try to set this up, we would just basically say B equals mu naught I theta divided by 4 pi r. I'm not going to go through the entire steps because it's actually a really easy integral. This angle is 90 degrees. So all around the entire arc, that thing is just going to be like sine of 90, which is just 1, so it's nice and easy. And then you get the 1 is the r vector, so literally you're just working at ds around whatever percentage of the arc. Let's say it was a full arc. ds around your full arc in integral is just going to be 2 pi r. So that's it. Okay, so that's the whole integral. And because this isn't the full arc, it's just over pi over 2, you can work that out. It's not too bad. Now over here for the full circle, that would actually cancel out. You'll get mu naught I divided by 2r. Okay, and so those are going to be some easy answers for this circular shape. Now let's look at this Helmholtz coil. We're going to try to figure out the direction and magnitude of the magnetic field there. First we got the I going in this direction. It's coming out of the page here into the page there. So we can kind of draw our little IDS right here off this arrow. Bam, it's kind of coming this way. And if we'd imagine the r vector going in this direction, well, let's try to figure out what the angle would be between if it was going flat that direction and we just went straight that way. Well, that's a 90-degree angle. Okay, so from there to there, it doesn't matter. It's slanted a little bit, but it's still a 90-degree angle between the IDS and the R. So there's your IDS right there, and then your R. But that's a 90-degree angle. So the sine of 90 is going to be 0 there. The 1 is going to be 1. And so all we got to figure out is the IDS around the entire thing, which I think is going to be 2 pi again, 2 pi r. So that's a pretty easy integral. But there's some other stuff we need to think about. If we were to try to follow through with this cross product and start to think to ourselves, okay, well, we're going to need to cross that way. Something's funny about my thumb. It's kind of pointing this direction, like here. And, okay, well, if I go over to the other side of this whole thing and I do that cross product again, I just kind of go like, okay, it will be this way, I have to cross that way. I'm noticing it's pointing in a funny direction. It's pointing this direction. So, okay, well, that means at the top and the bottom, those things should cancel, and I'm going to get a component really that's just going only in that direction, right? And if I want that component, I'm going to probably want this angle here, so that way I can take the cosine of that angle with respect to that force, and then I'll be able to get that direction. So it's very important that we don't confuse this angle. You gotta be careful here. You might confuse this angle with that angle and think that angle is the same as that angle, but it's not. Okay, so that angle is not that angle. That angle is not going to be the angle here. You might expect it to be this. If I just go like this and connect that side to that, doesn't that angle look like that angle? This one? But it's not. It's really important we don't get those two confused, because that'll give us the wrong answer. So it's not that angle. It's actually this one. Yeah, it's weird, but yeah, it's this angle. So if we know that angle, we want cosine of theta. Cosine of that is going to be r over r, big R over little r. Great. So that's what we'll go ahead and put over here, because that's a really important thing we have. So cosine, and this is going to be not of theta, because we kind of already used the theta during our integration process. I'll call this the angle phi. Bam. So cosine of phi is going to be equal to r over r. And I think I remember that I said the integral of the ds over here, ds, it would be 2 pi r. ds equals 2 pi r. So we're already making some good progress here. And then let's just try to figure out what the b is. B is supposed to be equal to mu naught I over 4 pi, and then we'll have the integral, and yeah, we got ds on top. We would have r squared on the bottom, and then we would have the cosine of phi. Okay, so just setting it up. So r squared is kind of hard to write. On the bottom here, we would see that it would be b equals mu naught I, and then on the top, we would have the cosine times the ds, right? So we get r times r, you're going to get r squared there. So that's cool. And then you would also get like a 2 pi somewhere on top. But on the bottom you got a 4 pi, so on the bottom you'll just get a 2. And then on the bottom you also have the r squared, and you also have an r there, so it's technically r to the third. We figured out what r was for this thing is going to be that. We know what the r to the third is supposed to be. It's going to be like that, x squared plus y squared 3 over 2. That's how that works out to be. And then, well, let's make this correct, because in this case it's not x squared plus y squared, it's going to be z squared plus r squared. So z squared plus r squared. Great. And then we also might want to consider how many loops there are around this. That's just one loop, but there might be more. So you could put n for the number of loops. And consider this. On the other side, from like a z distance away here, you're going to get the same type of thing happening. Like the magnetic field, it continues. It's all the way through here. So if you have another loop somewhere over here, then that point is just going to be doubled. So you might actually have to multiply this whole thing by 2 if you have one loop and then another loop. Like that would be like the center between two of these coils. And this is a pretty important answer. So I think that this is all the different integrals that we need to kind of know for the magnetic field so far. Now let's analyze the magnetic force. Magnetic force. Now it's annoying because the magnetic force and the magnetic field are not pointing in the same direction. It's kind of like torque. It's like pointing in a different direction. This makes things a little bit difficult. We're just going to say FB is equal to I and then L cross B. And there's a couple different equations for the force. We'll just start with this one. That's going to be on wires interacting with the magnetic field. So let's say we had a wire like this, and let's say that the magnetic field was pointing out of the page here. So it would be something like this. And we could call that B. And then I would like to say that the current flowing through this wire is 0. And that's essentially what's going to happen. You got your current sitting in a magnetic field. It's going to do nothing if there's no current. Let's say I wanted to run some current through these wires. And if I ran the current sort of in this direction, we notice this wire would start to bend because we got our magnetic field here still pointing out of the page. But when I do the cross product, here's the length, and it's coming out of the page. Then we notice that the thumb is pointing in this direction. We would get a force pointing that way. This is the FB. And we can also reverse that current, so we can go the other direction. We just notice that it's pointing in the opposite way. That way. And yeah, there's just going to be a force going in that direction if we have the magnetic field still pointing out of the page. Okay. Just going to use that cross product, L cross B. You'll find which direction the force is. So here I've set up a little current going in this direction, and it's going to set up its own little magnetic field due to this whole situation right here. As you can see, it point up there, and well, you get the opposite going in the other way. But let's say I wanted to pull another wire up next to it, somewhere like around here, and this one would have an IB. Now, because this wire is now all of a sudden finding itself in the middle of a magnetic field like this, then it's going to notice some kind of a force. Let's do the cross product. So we go going forward, and we're going into the page. So you would notice a force up on this one. And we're going to say FBA because it's pointing from B to A, like that. And they're going to find themselves a distance D away from each other there. All right. Now we could start to write out this force. FBA is going to be equal to IB. It's nice how we start with the B on the left side, and then we'll have the L cross BA. So you got your B on the left side, your A on the right side. It's pointing from B to A, so FBA. We can answer this a little bit more completely by saying FBA equals mu naught L IB IA divided by 2 pi d. Now there's another way to represent force, and that would be if there was only just a single particle. We could say F of B equals Q, and then V, the velocity of the particle, crossed with the magnetic field, and then that's going to be equal to QVB sine theta, the angle between those two vectors there. From this expression, we can actually derive some very strange formulas, like for example, B is going to be equal to FB divided by QV. So like that's just kind of strange. And then we could also say that E is equal to force of the electric field divided by Q. And we'll notice that these two things are almost the same thing. Force divided by Q. This one just happens to have a velocity component to it. This one doesn't. So let's imagine the impact of this force on an electron. So we're going to put an electron sort of going through here. Electron. That's the velocity of the electron, or the vector velocity. And we see that the B is actually pointing into the field. So we'll cross V with B and see what happens. We go that way, crossing it in, we actually get a force pointing up. So that's going to be the FB that this electron feels. So if it feels a force that direction, the electron, because it's a negative charge, it's going to actually go the other direction. So we're going to notice that the electron is going to start to move towards this side of the wire. And if we do that long enough, we start sending these things through, we're actually going to develop negatives on this side and positives sort of on this side, kind of. I mean, we wouldn't really have a positive, but you'll get a voltage difference between them. You could say that's 0 and that's negative, but still, you get an arrow pointing this way now. And as the electrons start going through there, they're going to want to go the opposite direction, sort of, right? Kind of. So we have this force already going this direction from the FB. And now this force is starting to get a little bit stronger. So at first it's really, really weak. So, you know, the magnetic force is going to still take over. But there's going to be a point where this force will grow to the point where it will match the FB. And then these two things will be actually equal. Or, well, this and this will be equal. And at that point, you can send an electron through there, or you can send a particle through that. It's got to have perfect speed. It's got to have the correct speed. If you want this stuff to cancel and you don't want any kind of influence from any one of these forces, it has to go at this proper ratio in order for this to go exactly through there with no influence. But let's notice that the force of the magnetic field is actually based off of the velocity of the electron. So the faster that you send this thing through, the greater this force will be. If you send this really slow, then this force is going to be really slow, so you just need a small voltage difference. If you send it through really fast, you need a higher voltage difference. Just an example. Or if you wanted to overcome this thing and make it turn a certain direction, you could adjust that force by adjusting the speed. And so there we go. This is the third way that magnetic force, can influence our equations. And we can actually figure out the directions of the forces in the fields by working backwards. First, let's imagine the electron moving around in a circle like this. If that was the case, we would be expecting a force, a centripetal force, pulling it inwards like this. So we would probably assume that would be the FB. And if that was the case, let's try to figure out what direction that the field would be. So in order to get a force in that direction, we would want to go move with the electron, and then we're going to cross it this way so that the force is in the opposite direction, because the electron is a negative particle. So the magnetic field would be pointing out of the page. All right, so that's that. Cool. And we can represent this FB kind of like this, QVB, and we know that's going to be equal to the centripetal force. So we could say that's equal to M v squared over r. Isn't that the centripetal force equation? Now sine of theta between E and B is going to be 90 degrees, so that will just go away. We've got QVB. That's from this equation here. And that's going to be the mv squared over r. Let's try to describe this radius by saying r equals, we'll rearrange this formula with r over there, and then we got mv divided by qb. And we'll notice that we have the r as a function of velocity, meaning that as the velocity increases, the radius increases. Well, that's interesting. That means that as the radius increases and goes further out, the velocity also increases. And it's a linear too, so that's interesting. Now, we've also got t equals 2 pi m divided by qb. And again, this is sort of showing you that the time that it takes for this to spin around has no relationship to the radius or the velocity, meaning that no matter where it is, either if it's really far out or really close in, it's got to rotate at the same time every time. So if it's in, it's got to go really, really slow, and if it's out, it's got to go really, really fast in order for that to be the same time. This is kind of weird this way. It's kind of the opposite of how planets work. But anyway, we got 1 over f also as the time. And that's how we can describe circular motion. Now I've drawn this little thing here called a cyclotron. Usually a particle will be like right in the middle here, and then there's this voltage difference here, which will cause an acceleration every time it passes that. And so, you know, you'll start your particle here, and then it'll start to spin around like this, and it'll just get really, really, really fast, and it'll just go through this, and then, you know, this is like a particle accelerator type of thing. There's some really important equations we probably want to know. Let's take a look at the total distance. If we want to find the total distance, then we would take the average circumference, and then we would multiply that by the number of revolutions. This is how we find the total distance. And then we would also want to figure out what this whole Q delta V thing is. Q delta V, that's going to be equal to the change of the kinetic energy. Every time it passes through there, you're going to get a small change of kinetic energy. Let's say we want to try to figure out what the number of revolutions was. Well, at the end, you would have this maximum velocity, which would give you a maximum kinetic energy. You take that max kinetic energy and you divide it by the delta KE that you get every time you boosted it. So that way you figured out how many times you boosted it. But keep in mind that you boosted it twice per revolution, so let's factor in that too as well. And so then you would get this equation that KE max divided by the delta KE, and then there's the 2 in there, that's going to equal the number of revolutions. So that's going to be this part of the equation. Keep in mind that you might need to figure out KE max mathematically, which would be 2 pi squared mr squared f squared. And then we could also figure out the Vmax with that whole concept, which would be 4 pi squared r squared f squared. Now let's say we want to figure out the next part of this formula, which is going to be the average circumference. You're going to need the average radius, so you can go 2 pi r. But the average radius, of r average, is going to be equal to the square root of 2 KE average times an m in there divided by 2 pi mf. Okay, and with that, you'll also be able to maybe try to calculate KE average, which is just going to be equal to the KE max divided by 2. And I think that should be all the equations we probably need to be able to figure out what a cyclotron does. One more thing about circular motion. Let's say you had an electron moving around like this, and the velocity was all like kind of weird like this. It would start off with a velocity here. It's like your initial velocity here. And you would also get this angle here to this axis. This is going to be your axis. If you're looking to find Vx along this axis, you would use v cosine theta, and this is the axial velocity. And if you wanted to find the velocity of the circular path, that would be, I guess we could call it vc. That would be v sine theta, and this would be the circumference velocity. One more little thing about circular motion. Let's try to relate magnets to what we're actually doing here, real magnets. So here, I'll try to draw one. It's going to look a little bit like this. We'll give it a plus up here, and then we'll go with the minus on this side. And we're going to have this little mu naught right there. We're going to call that the magnetic moment. Magnetic moment. And we also know that the magnetic field is going to be pointing out of the magnets from here, and basically it goes out of the plus and into the minus, just like the electrical field did. And then it'll also wrap around and kind of come towards the other side like this. And it'll do that a whole bunch of times. You get some spirals and stuff like that. But it's really important to note that the magnetic moment is pointing in that direction. So if we were to try to relate this to a circuit, here's the circuit now. Is going into the page over here and out of the page over here. And it's going to be coming along this direction like this. And through the center here, I can actually put one of those little purple arrows. This is another one of those moments. So mu right there. And that's the magnetic moment. We can use the right hand rule by wrapping our fingers with the current, and the thumb will point in the direction of the magnetic moment. So that is going to correspond to that, meaning that there's going to be a magnetic field coming out just like it was over here, and it would also kind of go towards the other side and stuff like that. And it would also wrap around. So that's kind of how magnets actually relate to what we're doing here with currents. So let's try to define this magnetic moment with an equation, and let's figure out what it can do for us. So we'll go mu equals N, I, and then A. Now this A is supposed to be the area of the loop, and the N is the number of loops that there is. And of course the I is the current. But what we can do is, if we stuck this whole thing in a magnetic field like this, let's say it was pointing into the page, I'll just draw a whole bunch of X's here. We're just going to stick this magnetic field in here. It's actually gonna experience a bit of a torque. So torque, and torque is going to be equal to mu cross B. So we got our mu, and we're going to cross it with B, so we get some torque in that direction. Essentially what this torque is going to try to do is it's going to try to align this magnetic moment with that magnetic field. Because notice how this magnetic moment is aligned with that magnetic field? Well, the magnetic moments and the magnetic fields like to be aligned. So there's going to be some sort of a force or a torque really trying to pull them towards that correct alignment. That's going to be that torque. And that's also going to be associated with some sort of energy, which is going to be U equals negative mu dotted with the B. And then if you wanted to figure out what the work was, well, work is just going to be delta U. Kind of should already know that. But these are essentially what the magnetic moment does for us. It tries to line up these currents with stuff and provide some torque. This whole next section is going to be dealing with Ampere's law. And that's going to be this little integral B dotted with ds. And we could try to call that B cosine theta ds. And this is going to be the angle between these two. We'll try to figure out what that means in just a second. This should be equal to mu naught I enclosed. And this should also be in units of Tesla meters. So I'm going to try to draw current right here, plus I, and then I will draw an Amperian loop around it, like this. The loop will be going in this direction. That will just be something I decide. Go in any direction that we want. But we also note that the thumb direction of current will give us the direction of the magnetic field. We know it's actually in this direction, this direction, this direction. So it's actually lined up 0 degrees to this ds, which means that that cosine should be cosine of 0. Cosine of 0 equals 1, meaning that we can actually just get rid of this whole thing. And one will be able to solve this. If we wanted to figure out what the magnetic field was at a particular point at that radius, BR, we would be able to say it's the mu naught I enclosed, and then we can actually divide the integral of ds over here, which would just be 2 pi r. And this is the Amperian, this thing right here, this is the Amperian perimeter. So this is, again, if we want to find the B at a particular point, particular radius away, it's just going to be that. Now let's say that you wanted to find like a portion of this I. Like let's say the I was kind of bigger like this, and you had all this here, and you were trying to find a smaller loop inside of here, so you only got that portion of the I. So here's again plus I out there. Well, in that case, then your I enclosed would actually be equal to I pi r squared, and that would be the small radius right there that we have. And then you could divide this by pi r, that would be the regular r squared. Let's just give you this portion of the enclosed current that you might look for. And let's say you wanted to really just integrate like a more complicated version. You can find the I enclosed by doing an integral from whatever point you wanted to whatever radius you wanted. If you know the j, you would multiply it by the dA of this particular thing. So we'll just call it, well, dA is supposed to be 2 pi r dr. So we'll just kind of simplify it to that right now. This is for a circular Amperian loop, a couple of different equations. Now I set up this little thing here. This is a solenoid. You can kind of imagine these things being connected a little bit right here, because it's going to loop around into the page, and then it comes out of the page. It's actually this like circular structure like this. But if we put our fingers in the direction of the current, we'll get the B's going this direction. And I want to try to figure out what that B is. So in order to do that, let me go ahead and draw a box, the Amperian loop, from here to there. I'll call this point A, the B, C, and a D. And if I wanted to figure out what that B was, use the same formula we kind of did before. I could basically try to integrate this. So integral from here to there, plus the integral from there to there, plus the integral from there to there, and there to there. Let's start doing that. If we integrate from A to B, B, and this is along the x-axis here, dot dx. Cosine, if we go along with that, the cosine is going to be 0, so that's just going to go away, and we're just going to be left with bx. And the distance here to there, we'll call A to B, that distance is going to be x. Alright, it's a pretty easy integral. Now, the next one, we'll go B to C. B dotted with dy in this direction. Well, there's no magnetic field. That way the cosine is 90. Cosine of 90 is just 0. So this answer is equal to 0. Same thing on the other side. But from, let's go from C to D now, maybe. B dx, that's this way. There is no magnetic field here at all. The only field is here. So if there's no magnetic field, that's 0, and this is also 0. And then we'll keep going here. We got from D back to A, B dy. Remember the same thing with a dy. It's cosine of 90, so this is 0. So the only thing we have here is the bx. And let's look at what the I enclosed for this solenoid thing is supposed to be. It's going to be I n divided by L, and then there's going to be an x. This is a little bit of a given thing here. We'll just say, so for the final expression here, what we could say is basically bx is going to be equal to mu naught I enclosed, which is going to be I n over L times the x. And well, look at that. The x's will cancel from both sides. So in the end, we'll actually just get that the b from the sol is going to be equal to mu naught I n over L. In this final bit, let's just try to upgrade that solenoid to a toroid. So at first, it was going to be this tube going straight, and now we're going to curve it around like this and basically make it into a loop. Well, the first thing we can notice is if we use the right-hand rule and we follow this around, look, the B, the magnetic field, is actually going to be moving along with it like this. So that's one part of this. And then we'll be able to draw a nice little loop in here. Run it the same direction if you want. So you'll get cosine of 0 and all that good stuff. You'll be able to basically use this formula right here, and you'll be able to say that B toroid is equal to mu naught I divided by 2 pi r. But here's the thing, you're going to have a lot of these different coils in there. You know, there's just 1, 2, 3, 4, 5. So you need to multiply this by an n up here. This is the number of loops that you're going to have in there. And this, remember, this is the amp perimeter. So the radius is going to be up to there. That's how you can find the B of the toroid. So I think this covers a lot of this stuff about magnetic fields. There's some more stuff coming up, but I think this is a good basis.